The most expensive decision a naval commander can ever make is the deliberate destruction of his own fleet. In maritime warfare, the ship is the asset you protect even when everything else is expendable. Thousands of man-hours, acres of oak forest, and a nation's ability to project force. To lose one is usually the definition of failure. And yet there is one narrow scenario where a ship's destruction stops being a loss and becomes a tool, a blockship. It's a one-way mission where the hull stops being transport and becomes terrain, dropped into a critical choke point to deny an enemy access. It is a one-way mission where the hull is no longer a vehicle for transport, but a massive, movable piece of terrain designed to be dropped into a critical choke point to deny the enemy access. In the late 11th century, the residents of Roskilde faced an existential threat. At the time, the city was one of Denmark's royal and ecclesiastical centers and a thriving hub of trade, sitting deep within the protective embrace of a complex fjord system. However, the geography that protected Roskilde was also its vulnerability. The fjord was navigable, and for any raiding fleet pushing in from the Baltic or the North Sea, the water was a highway leading directly to the heart of the kingdom. The defenders needed a gate. Since they could not build a stone wall across the surface of the water, they decided to build a wall on the seabed. The location chosen for this operation was the Peberrende Channel. This was a narrow, treacherous stretch of water that served as the primary deep-water lane for inbound traffic. The current here was strong, and the margins for error were slim. If a defending force could clog this specific artery, an invading fleet would be forced into the shallows where they would ground out or be easy targets for coastal defense. The engineers of the time did not use nets or chains. They used the heaviest, most durable objects they possessed. They used their own ships. The operation began with a ruthless selection process. The defenders identified 3 vessels that had reached the end of their useful lives, yet were still sound enough to be towed into position. These were not small fishing boats. One was an ocean-going cargo ship, built for open water and heavy loads. Another was a coastal trader. The third was a warship. Under normal circumstances, these hulls would have been stripped or broken up for firewood. Instead, they were loaded with the one cargo they were never designed to carry. Laborers hauled tons of flint and granite boulders onto the decks. The weight was judged carefully. It had to be heavy enough to pin the hull to the bottom against the scouring force of the current, but not so heavy that the ship sank too early during the tow. The pilots navigated these heavy, sluggish vessels out into the center of the Peberrende Channel. They aligned them across the current, broadside to the flow, to maximize the disruption of the water. Then they opened the hulls and let the water in. As the water rushed in, the ships settled. They did not crash violently. They slumped into the soft mud of the channel floor. Once they were submerged, the work was not finished. The team drove wooden posts into the seabed around the wrecks, and in places wove wattles between them, extending and strengthening the barrier. Over time, that lattice could also catch drifting sand and silt, helping the blockage hold its shape. The channel wasn't being sunk, it was being sealed. About 20 years later, the threat remained, or returned with new urgency. The original barrier had settled and shifted, so the command went out again. 2 more ships were towed to the site. One of them was a magnificent longship, a high-speed troop transport nearly 100 feet in length. It was a vessel of immense value, yet it too was sacrificed, filled with stones, and sent to join the pile. In total, 5 ships were stacked in the darkness of the channel. The blockade did what it was meant to do. It narrowed and controlled the deep water lane through the Peberrende, turning passage into a gamble for any large vessel that tried to force its way in. For Roskilde, the fjord now had a lock, built from hulls the defenders were willing to give up. But as the centuries passed, the political landscape changed. The threat of invasion faded. Roskilde remained, but the barrier was forgotten. The ships did not rot away immediately. The fjord mud was soft and silty, and as the hulls settled deeper, they were enveloped in an anaerobic embrace. The oxygen was cut off. The bacteria that usually consume wood could not survive. The 5 ships disappeared from the surface of the water and from the memory of man, becoming nothing more than a hazard to fishermen, a pile of stones that snagged nets and broke anchors. They lay there in the cold and the dark for 900 years, waiting for a new generation of engineers to realize that the obstruction on the bottom of the channel was actually a lost fleet. The fundamental enemy of any underwater salvage operation is not the depth. It is the visibility. In the clear waters of the Pacific, a diver can read a wreck from 50 feet away. In the Roskilde Fjord, the water is a suspension of silt, algae, and sand, coffee mixed with milk, where your hand disappears before your arm is fully straight. In those conditions, standard archaeology collapses. Working by touch, a diver might find a timber, but he can't map the relationship between thousands of fragments or even tell ballast stone from seabed. A recovery attempt would bring up wood while leaving the history behind. The lead archaeologist, Olaf Olsen, and the naval architect, Ole Krumlin Pedersen, made a decision that fundamentally changed the scale of the project. They realized that they could not adapt the diver to the environment, so they had to adapt the environment to the diver. They would not swim to the ships. They would bring the seabed up into the air. They proposed a massive civil engineering project, the construction of a watertight enclosure around the entire wreck site, a structure known as a coffer dam. In the summer of 1962, the tranquility of the fjord was broken by the rhythmic impact of a pile driver. The engineering team began to drive interlocking sheets of steel deep into the channel floor. This was a brutal industrial assault on the sediment. Each steel sheet was a vertical wall, driven down through the mud until it bit into the solid glacial clay beneath. The engineers outlined a broad sheet pile enclosure, enclosing an area of nearly 27,000 square feet. It was an artificial island of steel rising from the gray water, large enough to contain not just the ships, but the entire debris field surrounding them. The physics of a cofferdam are unforgiving. As soon as you seal the perimeter, you create a pressure differential. The water outside the walls is pushing in with millions of pounds of force, seeking any gap, any weakness in the interlocks. The steel walls had to be braced internally to prevent them from buckling under the hydrostatic load. The team built a wooden walkway around the perimeter, turning the top of the dam into a working platform. They brought in heavy electric pumps, the kind used in mining and construction, and positioned the intakes in the center of the pool. Then they threw the switch. The pumps roared to life, and for the first time in 9 centuries, the water level over the Skuldelev Ships began to drop. It was a slow, controlled reveal. As the water receded, the chaos of the seabed was exposed. It was not a clean, sandy floor. It was a vast, sludge-filled depression, a landscape of gray mud and black stones. The smell was ancient and pungent, the scent of decaying seaweed and biological matter that had been trapped since the Viking Age. By the time the water inside the cofferdam had been lowered step by step, the engineers had achieved their goal. They had taken the sea out of the archaeologists' way, without pretending the site could ever be treated like an ordinary dry pit. The ship parts emerged as the level fell, and the team worked from narrow wooden bridges laid above the wreckage, never walking on the fragile timber. But as soon as air reached the waterlogged wood, a more dangerous clock began to tick. The very act of exposure could begin to destroy what the excavation had come to save. The victory of the cofferdam created an immediate and lethal paradox. The engineers had spent months and a fortune in steel to pump the water out of the site, but the moment the seabed was exposed to air, they realized the clock had started. These Viking ships were no longer wood in any ordinary sense. They were black, spongy, and saturated, held together by the very water the pumps were removing. For 9 centuries, the ships had survived because of a specific environmental condition known as anaerobic preservation. When a ship sinks in shallow, oxygen-rich water, shipworms and bacteria consume the timber within a few decades. But the Peberrende Channel was different. The heavy silt and the rapid burial sealed the wreckage in an oxygen-free tomb. Without oxygen, the biological agents of decay could not function. The cellulose and lignin that gave the oak its strength had slowly degraded, but the physical bulk of the wood had been replaced cell by cell with water. The water was now the only thing supporting the cell walls. It was the skeleton of the ship. If that water was allowed to evaporate, the surface tension would drag the cell walls inward. The timber would not just crack, it would shrink, warp, and collapse into dust. The ships would effectively disintegrate before the eyes of the excavation team. The site required a solution that maintained the visibility of a controlled dig while preserving the moisture of a submerged wreck. The answer was not a high-tech industrial humidifier. It was a trip to the local hardware store. The team installed a grid of plastic piping across the entire excavation zone. connected to 19 standard garden sprinklers. Fjord water was pumped in and sprayed continuously over the exposed timbers whenever sun and wind threatened to dry them. Inside the steel walls, the work took place under an artificial drizzle, a muddy theater where oilskins and rubber boots were as essential as trowels and tags. The dig happened ankle-deep in sludge under a steady, punishing downpour that never let the timbers forget what they needed to survive. This constant irrigation was the only thing standing between the artifacts and destruction. If a section of timber was left in drying air even for a short time, the damage could be irreversible. The team had to be vigilant. If a sprinkler head clogged with silt or a pipe burst, the localized drying could snap a 1,000-year-old keel. The noise of the site was a constant, rhythmic hissing of water hitting mud, punctuated by the heavy thrum of the drainage pumps. Under this curtain of water, the texture of the wood began to reveal itself. It was soft, almost like wet leather. You could push a finger into the surface of an oak plank with little resistance. This fragility dictated the rules of engagement. You could not walk on the ships, you could not lean on them. Platforms and suspended gangways had to be built over the wrecks, allowing the diggers to hover above the mud. They were not just excavators, they were surgeons operating in a swamp. The environment was stabilized, the patient was on life support, but the ships were still buried under hundreds of tons of stone ballast. The next phase would require removing the very weight that had sent them to the bottom in the first place, without crushing the wet cardboard that lay beneath. The greatest threat to the survival of the Skuldelev ships was the very mechanism that had been used to sink them. For 900 years, the vessels had rested under a crushing overburden of flint and granite boulders. In the 11th century, these stones were a strategic necessity, heavy enough to hold the buoyancy of the hulls down against the current. In 1962, they were a kinetic hazard. The wood beneath them had lost its structural integrity. It had the consistency of wet cardboard or stiff cheese. A single stone, shifting its weight by a fraction of an inch, could shear through a plank or pulverize a delicate frame. The excavation team faced a high-stakes game of reverse engineering. They had to dismantle the blockade rock by rock without triggering a collapse in the timber beneath. Material moved out the hard way, hand to hand, bucket by bucket, and for the largest stones in sacks, because anything faster risked a mistake the wood couldn't forgive. The work was performed by a chain of volunteers, students, and archaeologists standing on the suspended gangways. They worked lying prone on the wooden planks, reaching down into the mud to feel for the stones. The visibility was better than underwater, but the mud still coated everything in a uniform gray slime. The excavators had to use their fingertips to distinguish between the hard, cold surface of the stone and the soft, yielding surface of the wood. It was a tactile minefield. If a worker pulled a stone that was actually wedged under a rib, the sudden release of pressure could cause the wood to spring up and snap. They established a bucket-brigade system. Stones were pried loose from the suction of the clay, lifted clear of the hull, and passed up the line toward the cofferdam walls. Under the relentless sprinkler rain, the job wasn't heroic in any cinematic way. It was arithmetic. Thousands of separate weights had to be removed, one careful transfer at a time, until the mound that filled the hulls and spilled across the seabed was gone, and the artifacts could finally breathe, without drying. As the weight was lifted, the true condition of the ships began to emerge. They did not look like boats, or like the proud, curved silhouettes in tapestries. The stones and water pressure had flattened the hulls into something almost two-dimensional, splayed open, pressed into the mud like blueprints. And time had finished the disassembly. The iron rivets that once stitched the overlapping clinker planks together had corroded away, the tension vanished, and the strakes slid apart. What lay in the channel was no single hull at all, but a scattered anatomy, ribs, keel sections, and plank fragments spread like an exploded view. Before a single piece could be touched, the chaos had to be documented. The team established fixed reference points around the cofferdam and used stereophotography to record overlapping images of the site, while broader views were captured from above to preserve the overall pattern. This record became their map. Move a fragment too soon, and you don't just lose position. You erase meaning. On the ground, the archaeologists crawled through the mud with white plastic tags. Every fragment, no matter how small, received a number. These numbers were pinned gently into the soft wood, turning the wreckage into a giant paint-by-numbers puzzle. The lifting process itself was a delicate operation. You could not simply grab a plank and pull. The wood was so degraded that the pressure of a human grip would crush the fibers. The workers had to slide thin sheets of masonite or plywood underneath the timber, creating a rigid stretcher. The wood was then lifted on this tray, never supporting its own weight against gravity. It was immediately wrapped in plastic and kept wet. If the water inside the cells evaporated, the artifact would be lost, so the transition from the mud to the storage tank had to be seamless. As the disassembly progressed, the complexity of the problem became apparent. The ships were not neatly separated. In the panic and urgency of the 11th century operation, the vessels had been sunk on top of one another. The timbers of one ship were entangled with the timbers of the next. As the excavators pulled up the long oak planks of the great warship, they found ribs from a smaller cargo vessel wedged underneath. There was a growing confusion about the count. They had identified a long, narrow warship they called Ship 2, and another similar vessel they called Ship 4. The pieces were mixed, the styles were identical, and the sheer volume of wreckage suggested a massive fleet. The mud was yielding its secrets, but it was doing so in a language the engineers could not yet speak. They were filling tanks with black, sodden wood, shipping the entire puzzle off to a laboratory where the real work of reconstruction would begin. The most dangerous moment for a shipwreck is not the collision that sinks it, nor the centuries it spends on the bottom. The most critical point of failure occurs in the laboratory immediately after recovery. The timber fragments of the Skuldelev ships arrived at the conservation facility in sealed, water-filled tanks, wrapped in plastic and anxiety. To the naked eye, the wood looked solid. It retained the shape of planks, ribs, and keels. But this was a visual illusion. At a microscopic level, the wood was a phantom. The cellulose and hemicellulose, the organic compounds that give fresh oak its rigidity and strength, had been almost entirely consumed over 9 centuries. What remained was a delicate grid of lignin, cell walls filled to the brim with water. If that moisture left, the structure would collapse. To stop this, the conservation team engaged in a long-term chemical war against physics. They needed a substance that could enter the wood, replace the water molecule for molecule, and then harden into a solid support structure that would hold the cell walls open permanently. The weapon of choice was a synthetic polymer known as polyethylene glycol, or PEG. PEG is a water-soluble wax. In its liquid state, it looks like thick, clear syrup. When it cools and dries, it becomes a white, waxy solid. The theory was elegant. Replace the water in the ship with liquid wax, then let it harden, but you cannot simply paint it on. The wax has to penetrate deep into the core of the timber, reaching the center of every single cell in a piece of oak that might be 4 inches thick. The process is one of the slowest in industrial engineering. The timber fragments were submerged in massive stainless steel vats filled with a water and PEG solution. Over a period of months and years, the temperature of the solution was gradually raised and the concentration of the wax was increased. It is a process driven by diffusion. The PEG molecules slowly migrate into the wood, displacing the water. It is a silent, motionless race against decay. If you rush it, the wax blocks the outer pores of the wood, trapping water inside the core. When that trapped water eventually evaporates, the inside of the timber collapses while the outside stays rigid, causing the artifact to tear itself apart from the inside out. For years, the Skuldelev ships existed as disassembled forms floating in heated tanks of chemical soup. The technicians monitored the specific gravity of the solution daily, watching the lines that signaled the wax was moving inward. It was suspended animation, a long, quiet interval between the wet world of the fjord and the dry world of the museum. When the process was finally complete, the wood was removed from the tanks and allowed to cool. The transformation was absolute. The timber was no longer soft and spongy. It was heavy, dark, and hard. The water was gone, replaced entirely by the waxy polymer matrix. The wood was now a composite material, a hybrid of 11th century biology and 20th century chemistry. It was stable. It could be handled, measured, and exposed to the air without fear of disintegration. The conservationists had successfully fossilized the fleet in wax. Now, for the first time, the pieces were rigid enough to be laid out on the floor of a large hall, allowing the architects to finally answer the question that had haunted the excavation. What exactly had they found? The initial inventory of the excavation site presented a mathematical contradiction that troubled the archaeologists for months. As the team cataloged the thousands of recovered fragments, they believed they were dealing with 6 distinct vessels. They had assigned designations 1 through 6 based on where the piles of wreckage had been found. Ship 2 was a collection of heavy oak timbers from a large warship. Ship 4 was a similar pile of oak found nearby. For a long time, the working theory was that these were 2 separate vessels of the same class, sunk side by side to anchor the blockade. But as the preservation wax hardened and the timbers were moved to the reconstruction hull, a physical impossibility emerged. The keel sections of Ship 2 and Ship 4 were not just similar, they were continuous. The grain of the wood matched perfectly. The wear patterns on the strake planks aligned with forensic precision. The engineers realized they had made a fundamental error in the underwater survey. They were not looking at 2 60-foot ships. They were looking at the bow and the stern of a single, massive Leviathan, a ship that had been split and scattered over time, then buried and rearranged by centuries in the channel. This realization changed the entire understanding of the find. When the 2 halves were digitally reunited, the vessel that emerged was not a standard Viking raiding craft. It was a great longship, a true dragon ship of the sagas. It measured nearly 100 feet from stem to stern. This was a superweapon of the 11th century, a vessel designed to carry some 60 to 70 men at high speed. It was a machine of such cost and status that its presence in a humble blockade seemed illogical. Why would a king sacrifice a capital ship to block a secondary channel? To answer this, the team turned to a technology that allows wood to speak its own history: dendrochronology. Every tree grows a new ring of wood each year. The width of that ring depends on the local weather conditions, rain, temperature, and sunlight. A wet year creates a wide ring, a drought creates a narrow one. Because the weather pattern is unique to a specific geographic region and a specific decade, the sequence of rings in a piece of timber acts like a biological barcode. By measuring the rings in the keel of the great longship and comparing them to master chronologies from across Europe, the scientists could pinpoint exactly when and where the tree was felled. The computer analysis returned a result that shocked the Danish team. The oak for the great longship did not grow in Denmark. Tree ring patterns pointed instead to southeastern Ireland, in the vicinity of Dublin and toward Waterford, and the timber was felled in late spring in May or June of AD 1042. The ship was not local. It was constructed in a shipyard in Dublin, a major Viking stronghold at the time. This discovery rewrote the political map of the blockade. This vessel had been built in Ireland, sailed across the North Sea, and served for 30 years before ending its life as a pile of rocks in a Danish fjord. It proved that the Viking world was not a series of isolated villages, but a connected maritime empire where high-tech hardware moved across oceans. The blockade was not just a pile of local fishing boats, it was a strategic disposal of international naval assets. The great longship, once the terror of the Irish Sea, had been used as the final brick in the wall that saved Roskilde. The final resting place of the Skuldelev fleet is a concrete and glass cathedral built directly on the shoreline of the Roskilde Fjord. Inside the Viking Ship Museum, the 5 reconstructed vessels float in the air, mounted on slender iron armatures that hold the blackened timbers in their original 3-dimensional geometry. They are not complete ships in the traditional sense. The preservation process saved the wood, but it could not replace the missing pieces. The hulls are ghostly, fragmented skeletons with vast open spaces where the timber had rotted away before the excavation. The viewer has to use their imagination to fill in the gaps, to see the curve of a strake where there is now only empty air. Yet, despite their fragmented state, these 5 hulls represent the most complete cross-section of Viking maritime culture ever discovered. They are not just a collection of boats, they are a functioning society frozen in time. We see the heavy, broad-beamed Canar, Skuldelev 1, the ocean-going semi-truck of the era, built for bulky cargo on long North Atlantic routes. We see the small, nimble coastal trader, Skuldelev 3, the workhorse that connected the local villages. We see the fishing boat, Skuldelev 6, the vessel of the common man. And we see the instruments of violence, the small warship, Skuldelev 5, and the magnificent great longship, Skuldelev 2. For the archaeologists, however, looking at the static remains was not enough. To truly understand these ships, they had to answer a question that the dead wood could not speak. How did they sail? The excavation gave birth to a new discipline known as experimental archaeology, using the detailed photogrammetry and the digital models derived from the wreckage. The museum boatyard began to clone the fleet. They did not use modern sawmills, they returned to the 11th century. They split oak trunks with wedges and hewed planks with axes, following the exact grain lines of the wood just as the original shipwrights had done. They forged iron rivets and wove wool sails. The most ambitious project was the resurrection of the Great Longship. Named the Sea Stallion from Glendolau, this 30-meter reconstruction was launched to test the capabilities of the ultimate Viking war machine. The results were terrifyingly impressive. The Sea Stallion proved that the longship was not just a troop transport, it was a high-performance sailing and rowing weapon engineered for speed. Under sail, the flexible hull rode the waves like a living creature, absorbing the energy of the sea rather than fighting it. In ideal conditions, it could surge past 15 knots, with an estimated maximum under sail around 17 knots, astonishing speed for an open warship driven by oars and wind. In 2007, the crew sailed the Sea Stallion from Roskilde all the way back to Dublin, completing the circle that began in 1042. The voyage didn't just honor the archaeology, it made the distance real. The irony of the Skuldelev ships is profound. They were built to move, to explore, and to conquer. Yet their greatest service to history came when they were stripped of their masts, filled with stones, and forced to stay in one place forever. The blockade of the Peberrende Channel was a tactical suicide mission that succeeded beyond its commander's wildest dreams. It was built to choke off the approach from the sea, helping protect Roskilde from any hostile fleet that tried to push up the fjord. And by sealing the ships in the anaerobic mud, it stopped the clock of decay, saving the technology for the 20th century. The barrier that was built to close the fjord eventually opened the door to the Viking Age. Today, the ship stands silhouetted against the gray light of the Danish sky, no longer guarding the channel, but guarding the memory of a civilization that used the ocean not as a barrier, but as a road.